Hey guys, looking at the warm-up from our 1.4 set of notes. We're asked if you heard an assembly line machine was running continuous, keyword there, continuous, for the last 40 hours, what could you kind of pretty much say about that assembly line? Well, what we could kind of say is over the last 40 hours, pretty much if this thing's running continuous, that means we didn't stop at all. So the assembly line didn't stop at all. Because in the real world, there's usually like maintenance issues, or a lot of times they need to kind of clean some of the machinery. But sometimes they have stretches where they can literally just keep going and keep going and keep going. And the whole purpose of this kind of warm-up is to kind of lead us into this analogy because functions actually behave very, very similarly. When we're looking at the definition for what a continuous function is, it really has to fit three different criteria. We're going to talk about what those are in just a second, but I'm going to very quickly go ahead and draw a rough sketch to kind of help us illustrate what's going on with these three different criteria. So here is our x-axis and y-axis. All right. So for a function f, it's supposed to be defined on an open interval, and what this is simply saying is that x could be any particular a value. So this a value can actually change depending on where you're at for your function. And we say that f is in fact continuous specifically at any a value when the first of the criteria happens to be when f of a exists to begin with. So in other words, what that means is this is actually something back from Algebra 1. Like let's say we had the line y equals x plus 2. We'll just go with that function. If you were to go ahead and throw in like this 0 in other words, if a was 0, you throw that in there, we'd end up with a y value 2. And notice that that is a specific point, that point actually does exist in our xy coordinate plane. Likewise, if you were to throw in the number 1 into this function, you end up with a y value 3. So again, another point that definitely exists. You're throwing in different x values, or particularly a values. They're kind of the same idea. And then it just has to exist to begin with. All right. So what happens with this function, if you think back to Algebra 1, there are a ton of points that would satisfy this function. In fact, actually, there are technically an infinite amount of values that you can plug into this function and get what this overall image is. Again, because this line is just comprised of all these different points that kind of line up. So again, the first criteria is when you throw stuff in there, it has to just simply exist. All right. And we have seen cases from our 0.2 set of notes where you tried throwing values in and it didn't exist, like an undefined statement having vertical asymptotes or holes, or a prime example of where things just don't exist. The second criteria would be the limit as x approaches the specific a value that we're hoping for of our function exists. So in other words, let's say, for example, we have this point right here. We're looking at 1, 3. If you go ahead and throw in that value, it does in fact exist. We ended up with that point 1, 3. Likewise, so I'll just kind of, that's for the second criteria. Secondly, the limit as x approaches 1 of our function does in fact exist. Notice the left side does in fact meet up at the right side. So that limit does in fact exist. All right. Now the third criteria is simply where we take these two first, the first one and the second one, and simply set them equal to one another. So the limit as x approaches some a value of our function is equal to our f of a. In other words, the limit is equal to literally the point when you throw it in there. Now, a pretty good analogy of this is if I was to just say, like, okay, this is, and let's actually change that color. Let's erase these. So we can kind of see them all in action together. There we go. All right. If we had, for example, the first criteria, f of a exists, well, here is that point. Then the second criteria comes in. As long as the left side is in fact meeting with the right side, that limit does in fact exist. And now the third criteria is pretty much just saying, hey, they meet up at the exact same spot. And there it is. A case, so as a result, this would then be a continuous function because it was defined there originally, the left side is meeting up the right side, and they are in fact equal to one another. So that is pretty much continuity in a little nutshell. Now, there are cases where maybe one of these fail. So for example, if we had like this existing, I'll go ahead and erase this. The limit exists, the left side does in fact meet up with the right side, but we see the first scenario, maybe instead of our point being where it's supposed to be, maybe we have a hole existing at 1, let's say 5. All right. So you can kind of see this jump in continuity, and as a result, that would not be continuous. The first one exists. The second one even works. The limit exists, but they're not ending up. It's failing criteria 3, where they're not actually ending up at the same spot. So that would be an example of a discontinuous function. Another one would be just kind of like an undefined statement. All those functions, rational functions that we saw in defined things. So, as long as it meets all 3 of these criteria, it is said to be, as long as it meets all 3 of these criteria, it's said to be continuous. If it doesn't meet any single one of these criteria, it is said to be discontinuous. Oops, discontinuous. Specifically, thought I was missing a U in there. Yep. At that particular A value. And A can be really anywhere as long as it's on your interval that you're talking about. So again, we just kind of used 1 as an analogy to kind of go over this example. But again, recapping, the original function has to exist when you throw it in there. Can't end up with like a hole or undefined statement, something over 0. Criteria 2, the limit as x approaches that particular a value of that function has to exist. So in other words, the left side has to meet up with the right side. And then finally, criteria 3, they both have to end up at the same spot. So this point would have to be down here for that to be continuous. So again, though, that is the definition for continuous and the warm-up from our 1.4 set of notes.